Last time we looked at Yao's protocol, the passively secure variant for two parties. We looked at how you make the Yao protocol more efficient by free XORs and other techniques, and we kind of passed off the problem of making it actively secure. So that's what we're going to do today. So what do we mean by making something actively secure? What we mean is that the adversary, one of the players, cannot deviate from the protocol without the other player either aborting or working out that something's going on. So you can't cheat by deviating from the protocol. That's what active security means. So why isn't Yao actively secure? Well, we've got two players. We've got the evaluator and we've got the person who creates the circuit creator, the garbler. Now the evaluator doesn't really do anything. He gets his input, that's it, and then he just evaluates the circuit. There isn't really much he can do that will stop, that will break the security of the other player, the garbler. Okay, so that's assuming that the OT protocol is actively secure, which we kind of brushed under the carpet, but let's not worry about that for the moment. However, from the point of view of the garbler, there's lots he can do. So the classic attack is that he's meant to be creating a circuit for this function here, where he's going to get the output value y1. But what happens if he changes the function being computed to this function, which produces in his component the secret input of player 2? In that way, when player 2 evaluates the circuit obliviously and then sends back the garbled output table for player 1's output, then player 1 just learns player 2's input, which is not what we want. So to solve this problem, we're going to look at a three-party protocol first, and then look at a two-party protocol. The three-party protocol is a bit easier, and the three-party protocol will protect against one active adversary. But before we do that, we're going to look at commitment schemes. Now, commitment schemes are a very basic cryptographic construction. A commitment scheme commits to a message, and it produces a commitment value C, the commitment, and an opening data O. And then what happens is later on, you take the commitment, the person who's committed reveals the O value, and then you can check that the commitment is correct, that it was the committed value, and that the message is the thing that's encrypted underneath it. So there's two security properties we want of a commitment scheme. We want that no information leaks about the message given the commitment. So without the opening data, you learn nothing about the message. So in some sense, the opening data acts like a key, and the commitment acts a bit like an encryption scheme. However, we don't really need to decrypt because we're only really going to do this once. But we do require that the committer can't change his mind. He is committed. Okay, so what we require is that you cannot find an M and an O pair and another M dash and O dash pair such that the opening for a given fixed commitment will give the two different messages out. That's really crucial, that the committer is committed. So the most trivial commitment scheme is to actually just hash. Okay, so what you do is you just take the message M, you take R is some 120-bit string just to randomize it, and then the commitment is the hash of the message given the randomness, and the opening data is the message and the randomness. Now what happens when we open, we hash that opening data and check whether it's equal to the commitment or not. And if it is, then we're fine, and what we can do is just take the first we can get rid of the last 128 bits, the first length of O minus 120. So we take the first chunk of the message of the opening data, and that gives us our message. Okay, and this commitment scheme is very trivial. It's hiding, assuming H is a one-way hash function, and it's a committing, assuming H is a collision resistant. So now we've got enough to look at our three-party Yao protocol. So we're going to have a three-party Yao protocol. So we're going to have three players, P1, P2, P3, and we've got a function f x1, x2, x3, where x1 comes from party 1, x2 comes from party 2, x3 comes from party 3. To make things simpler, we're only going to assume that party 3 gets output. It just makes things a little easier to explain, but that's easily fixed. Okay, so the first thing we're going to do is we can take this function f, and we're going to define a new function of 4 inputs. Okay, so we're going to create a fourth input. So the new function g is going to take x1, x2, x3, and x4, and it's going to be applying the function f, where you take the third input is actually x3 XOR x4. And now we're going to garble And then we have this garbling function, f of r, okay, which is going to just be our normal garbling thing that we normally do. We kind of go through the gates, encrypt all the gates as we did last time. Okay, so the first thing we do is that party 3 is going to take his input and split it into x3 and x4. And he's going to send x3 to player 1 and x4 to player 2. So clearly, if there's only one bad guy, P1's not going to learn anything about his input, and P2 is also not going to learn anything about player 3's input. Now what happens is P1 generates a random seed and sends it to player 2. And now, given this random seed, they both garble the circuit independently. But they're garbling the same function using the same randomness. So they should, if both act honestly, get the same garbled circuit out. This garbled circuit is sent by player 1 and player 2 to player 3, along with commitments to all the possible input wires and the output wire tables. So P1, so at this point P3 can check whether the two garbled circuits are equal, but that's fine. So P1 also decommits to player 3 their input values, okay, and the input values in x3. And P2 also decommits to their input values and the input values in x4. So P3 now has two garbled circuits, which are identical. He has the inputs corresponding to x3 in terms of the garbled labels. He has the inputs, the garbled labels corresponding to x4. He has them corresponding to x1. He has them corresponding to x2. So P3 can now evaluate the garbled circuit and get the output. Very, very simple. What can happen? Not much. Okay. Notice that P3 can do nothing to disrupt the computation. He just evaluates stuff. So he acts a bit like the evaluator in the two-party protocol. Now, if P1 or P2 lie about the circuit, then P3 is going to catch them. Okay, so because the two circuits aren't going to be equal. So P1 and P2 can't lie about the circuit. So that's fine. Now, if P1 or P2 lie about a decommitment, then P3 is going to catch this because the commitment scheme is committing, yeah, so they can't change their mind about a label later on. The problem is that the order they send the commitment values in we're going to reveal whether they've opened the 0 bit or the 1 bit. So what they have to do is they're going to have to randomize the order that they send the commitment to each wire label, input wire label, whether they send it in first 0 and then 1, or first 1 and then 0. So to fix this problem, what they do is they randomize the order, so you can't turn anything about that this is the first one, therefore corresponds to 0. And to do this randomization, they use the same random string R. So now P3 is going to get commitments in a random order, but the random order will be the same of the commitments sent from P1 and the commitments sent from P2. And if the commitments are randomized using the same string, then the commitments are equal. So P3 can check whether everything that P1 and P2 have done is secure, is the same, okay? We don't need to permute the bits corresponding to x3 and x4 because P3 basically knows what they are, yeah? Okay, so now that gives us our three-party YAO protocol. Kind of cool. We just have to evaluate one garbled circuit, but we have to produce it twice, once by P1, once by P2. But it's pretty simple, and there's no OT. If we're going to move on to the two-party YAO protocol, we're going to need a short diversion. We're going to need an extra protocol, which we're going to do string comparison. So how do we do string comparison? Okay, well, we can actually use OT, which is kind of cool. So what we've got is let's assume we've got player 1 who's got a bit string x1 to xn, and player 2 who's got a bit string y1 to yn, and they want to test whether the two strings are equal. So what we're going to do is present a protocol that gives P2 this information. For P1 to get the information, we just run the protocol in reverse, so that's kind of easy, yeah? Okay, so the protocol goes as follows. P1 is going to generate 128-bit input strings corresponding to each of these bits he wants to compare. And now we're going to run n OT protocols to compare these bit length n bit strings. Party 1's input to the ith OT is these two strings. Party 2 input is his bit. So what happens is party 2 learns Ri to the Yi for his bits. Party 1 can now produce the XOR of the complete sequence of bits that they've got. Party 2 can compute the same XOR, and now when Party 1 can send Party 2 the value x, and it's going to be equal to y if the two strings are equal, and if it's not equal to y, then there's something wrong. The two strings are different. So this is kind of a nice, very simple string equality check that requires compares n bit strings of length n using n OTs. Given that, we can now move on to a two-party YAO actively secure protocol. Now, okay, this is difficult. We're only going to give a sketch. Also extending YAO in an actively secure way for more than two parties, where you want to secure against a dishonest majority, not the 1 out of 3 case we just did. It's also difficult, but this is where we're just going to give a sketch for the two-party case. So why is YAO insecure in a two-party setting when we're thinking of active security? That's because the garbler could garble the wrong circuit. So an obvious solution to this is we let both parties garble the circuit. So both parties, one party acts as the garbler to the other one's evaluator, and then the other way around, the first party acts as the evaluator to the second party's garbling. So that's the basic idea. That's what's called dual execution. So dual execution is, we first kind of changed the protocol. So instead of computing the function of fx1, x2, we actually kind of randomize it a little bit. So we actually get, we want to produce it so we actually get the output kind of encrypted in some way. So player 1 is going to input some random number r1 and get the get his output y1 evaluated as y1 XOR r1. Okay. So that's the basic trick that we're going to do. Okay. Now, what we're going to do is we don't need now, when we execute it via YAO's evaluation, we don't need P2 to send the garbled outputs back to P1. Because what happens is P2 is going to evaluate the circuit. Remember, P2 in the original protocol is the evaluator. So he evaluates the circuit and he gets y1 XOR r1 and y2 XOR r2. Now, he knows his value of r2. That was one of his inputs. So from that, he can automatically compute y2. But the value y1 XOR r1 is a one-time pad encryption of P1's output. So he just sends that encryption back. He knows nothing what it could be. And then P1 can just obtain y1 because he knows r1. So splitting the function into this way allows us to avoid having to send the garbled outputs back, and we just send the actual output of the function. So what happens here is the evaluator learns the complete output of the function and not just a component and has the other player get the rest back. So kind of simplifies the construction in that we just have the garbler and an evaluator, and the evaluator gets the output. Okay, so now what we're going to do is going to compute G in two ways. One where P2 acts as the evaluator for P1 circuit, and one where P1 acts as the evaluator for P2 circuit. Now, so what's going to happen? So in the first evaluation, let's look at what happens to P2. They're going to obtain y2 XOR R2 in two ways. Once on their own, and once from P1's evaluation of P2's circuit. Now, if these two values are different, then P1's circuit creation was invalid. Okay, so they're going to get y2 XOR R2 in two manners. Okay, and in the second evaluation, P1 is going to obtain y1 XOR R1 in two manners. So we've got this dual way. You get once when you evaluate the circuit on your own and you basically get the value from evaluating the circuit, and once when you get it because this value is sent to you from the other player, and you know the value that's coming back must be correct, is because you've created the circuit. So your circuit is correct, it's gone to the other player. If the player lies by sending y1 XOR r1 back to you incorrectly, then you kind of know he's cheated. But if he is if he does send it back correctly and you get an incorrect value from your evaluation of the circuit, you know the circuit's wrong. So that solves at least one problem, okay? But we have an obvious attack. Again, we have an attack. So we suppose P1 is the adversary. So we still got the same attack, because if P1 could still send a garbling of the function. Instead of sending the function that he should do here, he sends a garbling of the function, which basically sends back an encryption of P2's input. So we still got this problem. We haven't really got rid of it. We just kind of shifted it to another place. So we need to basically solve that problem. So to do that, what we do is we do the equality check without sending the values back. So if we look at what happened here, the reason this is an attack is because player 2 is going to send this value back. So player 2 is going to evaluate the circuit sent by player 1 and then send this value back. So we want to stop all values that player 2 learns from player 1's circuit coming back, because then there's no back channel that can be used. Okay. So why did we have this value sent back? Because we wanted to compare 2-bit strings. But we know how to compare 2-bit strings. We just did that a bit previously. So this being able to check the equality of 2-bit strings is exactly what happens, and this is how we can solve this problem. Okay, so P1 will, if P1 is the bad party creating a bad circuit, P1 will get the valid output, but P2 is going to reject, since an invalid circuit is going to likely not give the same output as what P1 obtained. And P1 has to commit to this circuit before it knows P2's output. So we kind of have a protection. So that's sort of, we seem to have solved the main problem in the original Yao's protocol, in that you could lie about the circuit. Not quite. Now imagine you didn't want to learn the whole input of P2, you just wanted to learn the first bit. So it's called the first bit of X2Z. Now, so instead of creating a circuit which reveals all of X2, we could actually reveal the circuit. We could create a circuit for player 2, so player 1 can create this circuit, which basically tests whether the first bit is equal to 0 or 1. It's because the equality check will fail if the bit is equal to 0, and it will pass. Sorry, the other way around. The equality check will pass if the bit is equal to 0, and it will fail if the bit is equal to 1. So this is what's called a selective failure attack. You learn a bit of information from whether the other party aborts or not, or whether even you abort or not. So this is what's called a selective failure attack. So we've got this other attack. We seem to it's a less attack. It only reveals one bit of information, but it's still an attack, and we have to protect against it. Now that worked because P1 could still send P2 a bogus circuit. So instead of sending a bogus circuit, we need to make sure it's the real one. And the way to do that is we actually send 2 circuits. So player 1 gets 2 circuits, sends them to player 2. So player 2 now has a circuit G0 and a G1. Player 2 now flips a bit, and he asks P1 to either reveal the randomness used to generate circuit G0 or reveal the randomness used to generate circuit G1. And then, given this randomness has been revealed, P2 can now check one circuit is correct and then uses the other one to evaluate. So you've got 2 circuits. One he uses to check it's the correct function, and one he uses it to evaluate the circuit. So what can P1 do? He can create a fake circuit on one of them that actually does the attack. But with the 50% probability, player 2 is going to pick that circuit to do the checking. So he's got to kind of play the odds and hope that the circuit that is not opened completely is the one that's actually going to be doing the evaluation. This is a standard strategy in cryptography, and we can reduce this tuning probability to 50% by actually producing a lot more circuits. What we do is, instead of producing 2 circuits, player 1 produces S1 circuits. Okay, and now player 2 says half of them he wants to open. So he divides these S1 circuits into S1 over 2 circuits which are going to be evaluated, and S1 over 2 circuits which are going to be checked. So he opens, all the checked circuits are checked and opened, and then the evaluated circuits are evaluated, and then you take the majority verdict as the answer to whatever the output of the function is. So what's going to happen is, to win the game, the adversary has to get all the open circuits to be good, which is going to be hard. And then he's got to get the majority of the evaluated circuits to be bad, because otherwise he's got to make sure that they are all identical and they evaluate to the bad version of the function that he's trying to get the honest guy to evaluate. So actually the probability you get all these things evaluated is about 2 to the minus S1 over 4. And the idea is that if about half are good and half are bad, a single bad circuit is not open with probability of halved, but we need all the bad circuits to agree on the majority output. Thus we need more than S1 over 4 bad circuits not to be opened. And you can do a bit better analysis on that and get a better value for S1 that's better than 2 to the minus S1 over 4, but we can keep that as our basic idea. Why take the majority? The thing is if player, if you're bought, you know you're being cheated and you leak information. So what we want is we want player 2 never abort. So we always take some output. Thus, by taking the majority rather than just aborting if they're different, we stop this attack of you just detect when someone aborts, okay? Because the protocol might be inside of a much bigger thing. So that solves most of the problems, but we've still got problems. There's an attack on the OT, yeah? How do we attack the OT? So player 1 can still learn a bit of player 2's input with 100% probability. Because what we do is we just change the value that we put into the input wire. So we kind of do for the R0, the thing that we're sending over, that's the correct. The 0 bit is sent over as the correct input wire, input label. But the input label for the bit 1 is sent over as completely fake. And this happens is that if P2's input is 0, then the protocol is going to succeed. But if P2's input is 1, then the protocol is going to be rubbish because P2 is going to evaluate garbage. There's going to be garbage on the output and it's all going to be nonsense. So we've still got an attack there we have to fix. And the problem here is that each OT corresponds to a single input wire. So what we do is we kind of now randomize the input wires. So we kind of break each input wire into S2 different input wires, such that input sum x1 is the sum of S2 input bits. And now if a bit in the OT is wrong, it's always going to be wrong with very, very high probability. So you can't solve fix your probabilities here to get it to work. But we have another problem. Recall that we've got S1 circuits and we're going to evaluate them. Sorry, S1 over 2 circuits, we're going to evaluate them. Okay, and if the input size is L bits, then we're actually going to send L times S2 OTs. But the problem is that the attacker could send different inputs in the different executions on the same input bit. So he could kind of get one circuit evaluated for one set of inputs or one circuit evaluated for other. So what we need to do is stop that happening, and the way we do that is you basically send instead of sending L times S2 OTs, you send them only as L OTs. So you send, for each input bit, you send all of the circuits in one go. So that's a kind of nice simple fix there. And then this goes on. You have this attack and fix, and luckily this terminates. And you can also provide more optimizations on the actively secure system. So all that we've done previously is just give a kind of idea of the methodology of this attack and fix until you get a full protocol. And in the end, you can produce an actively secure computation of YAO, which is both practical and efficient. And it can easily evaluate circuits of many billions of gates quite easily. So this is a kind of some runtimes and just shows how things have changed over the last few years. So if you think of evaluating the AES circuit using YAO, so we write the AES circuit down, which is the standard test in this case. So in a passively secure protocol in 2009, it took 7 seconds to evaluate it with a two-party YAO protocol. With the actively secure version, which is very similar to what I just described, taking well over 1,000 seconds. This was really slow. And then over time, passive securities come down to 4.5 seconds in 1 year later. And then, only 8 years later, we're down to 1.4 milliseconds. If we go on a bit more, we could actually got actively secure evaluations of the A circuits, which are being executed in 15 milliseconds or 0.9 milliseconds. So these are kind of different here because they're kind of using different protocols, different trade-offs, etc. So we really are now able to, at the millisecond, actively secure evaluation of AES. So I hope that's given you some idea of how we do actively secure YAO, and I hope that's useful, and we'll see you next time. Bye.